A spacecraft could cross our solar system in a single afternoon. This dream of impossible speed pushes against the universe's strictest rules. The absolute speed of future spacecraft is not an engineering puzzle alone. It is a fundamental question written into the fabric of reality itself. By the end of our journey, you will understand the true cosmic barriers that guard the stars and the radical ideas that might one day slip past them. We will confront a universe where time stretches like taffy for fast-moving crews, and where empty space itself fights back against velocity. We will ask if the ultimate limit to our journey is a law of physics or a limit of our own imagination. What does it truly mean to travel fast in a cosmos that is constantly rewriting the map? That flashing finish line is not a trick of the track. It is the architecture of the universe. At the heart of this cosmic rulebook is a single, staggering number, approximately 299,792 kilometers every single second. This is the speed of light in the pure emptiness of space, and it is not merely fast. According to Albert Einstein's theory of special relativity, it is the fastest anything can ever go. This is not a suggestion or a temporary hurdle for our technology to overcome. It is a fundamental property of reality, as built in as gravity or the passage of time itself. Think of it this way: as any object with mass like a starship moves faster and faster, something strange happens from the perspective of the universe. Its mass does not stay constant. It begins to increase. The closer you get to that ultimate speed, the heavier you become. At 90% of light speed, your ship would have more than double its resting mass. At 99.9%, it would be over 22 times heavier. This increasing mass means you need exponentially more energy just to gain the next tiny fraction of speed. To actually reach 100% the speed of light itself, the math delivers a chilling result. Your mass would become infinite, and the energy required to push that infinite mass would also be infinite. It is a cosmic checkmate. No amount of fuel, no matter how efficient, can supply infinite energy. This principle forms the unshakable bedrock of modern physics, and it places a definitive, immovable cap on any form of conventional travel. The dream of simply pointing a ship at a star and accelerating until you get there is forever out of reach. This forces a profound shift in our thinking. If we cannot go faster than light by pushing through space, then perhaps the answer is not to fight the universe's rules, but to understand them on a deeper level. What if the path to the stars is not about speed at all, but about something far more subtle? But this cosmic speed limit brings with it a strange and deeply personal consequence. A journey at near light speed would not just change your position in space, it would change your relationship with time itself. To understand this, we can think of two identical twins. One stays safely on Earth, while the other boards a starship for a journey to a nearby star at a significant fraction of light speed. For the twin on Earth, decades pass. They watch the seasons change, raise a family, and grow older. But for the twin on the ship racing through the cosmos, something profoundly different is happening. Time as they experience it is flowing more slowly. Each second, each minute, each year for them is stretched out. When the traveling twin finally returns home after what felt like a voyage of only a few years, they step out to a world that has aged decades in their absence. Their earthbound sibling is now much older, a parent or even a grandparent. This is not a thought experiment. It is a direct and unavoidable prediction of Einstein's relativity called time dilation. The faster you move through space, the slower you move through time relative to someone who is stationary. For a crew on a ship traveling at 99% of light speed, time would pass at only about 1/7 the rate it does on Earth. A 5-year mission for them would mean 35 years have passed back home. This creates a staggering isolation. A crew could travel to a star 100 light-years away, spend a year exploring, and return, all within their own lifetimes. But when they come back, over 200 years will have passed on Earth. Everyone they ever knew, every culture they understood would be gone, preserved only in history books. They would be pioneers in the most profound sense, cut off from the very civilization that sent them. So time dilation presents us with a double-edged sword. It makes the galaxy accessible to human lifespans from the crew's perspective, a kind of loophole in the vast distances, but it does so at a tremendous psychological and social cost. It transforms a mission of exploration into a one-way trip through time, severing the travelers from their own era. This forces us to ask a difficult question. Is a journey truly successful if the explorers can never truly come home? The universe offers a path to the stars, but it may demand the ultimate price, leaving your own time behind forever. That profound isolation through time is only one side of the cosmic price tag. The other is an energy bill so vast it defies earthly comparison. To accelerate even a single gram of matter, a tiny paperclip, up to 90% of light speed, would require an amount of energy comparable to the entire output of a large nuclear power plant running for several hours. Now scale that up to a starship weighing thousands of tons. The numbers quickly become not just large but meaningless, dwarfing all the energy humanity has ever produced across its entire history. This is the propulsion energy crisis, and it begins with a simple, stubborn truth from Isaac Newton. An object at rest wants to stay at rest. This tendency, called inertia, is the universe's quiet resistance to change. To overcome it, to make a starship move, you must apply a force, and to make it move faster and faster, approaching the cosmic speed limit, you must apply a truly monstrous amount of force continuously. The problem is that our current tools are like trying to cross an ocean with a rowboat. Chemical rockets, the workhorses that took us to the moon, are spectacularly inefficient for interstellar travel. The best they could ever achieve is a tiny fraction of 1% of light speed. A journey to the nearest star would take tens of thousands of years. We must think far beyond burning fuel. Theoretical concepts like nuclear fusion, which powers the stars themselves, or the legendary antimatter engine, where matter meets its opposite in a perfect conversion to energy, offer hope. But even these face colossal, perhaps insurmountable, hurdles. The engineering to contain a sustained fusion reaction at the scales needed for propulsion does not exist. Creating and storing enough antimatter without it instantly annihilating with any normal container is a nightmare of physics and engineering. And here is the cruelest twist of relativity. The energy needed does not increase in a straight line. It scales relativistically. Pushing from 10% to 20% of light speed takes a certain amount of energy. But pushing from 90% to 91% requires vastly, exponentially more. As you near the ultimate barrier, the energy curve shoots toward infinity. Every extra kilometer per second costs more than the last, a law of diminishing returns written into spacetime itself. So this energy crisis is not just an engineering challenge. It is the most immediate and daunting physical limit staring down any blueprint for a fast starship. It demands we stop thinking about better rockets and start dreaming of entirely new principles of motion, of ways to generate, store, and wield power sources we can barely imagine today. The question shifts from how fast we can go to how we can possibly find the power to even try. This logistical nightmare has a precise and devastating mathematical form. It is called the rocket equation, and it was first understood over a century ago by a visionary Russian schoolteacher named Konstantin Tsiolkovsky. His insight was elegantly simple. and its implications are brutally limiting. A rocket works by throwing mass backward to push itself forward, but to accelerate that initial mass, you need fuel, and that fuel has mass of its own, which also needs to be accelerated. So you need even more fuel to push that fuel. This creates a chain reaction of weight, a pyramid of propellant where each new layer exists only to push the layers beneath it. The rocket equation captures this vicious cycle in a formula, revealing that to reach a higher final speed, the rocket's mass ratio, its starting weight compared to its empty weight, must grow not in a straight line but exponentially. Think of it as a cosmic tax on ambition. For a modest trip within our solar system, the numbers are challenging but manageable. But for the dream of near light speed, the equation breaks down into absurdity. Even with a theoretically perfect engine that converts 100% of its fuel into thrust, the calculations yield a result so staggering it borders on the philosophical. To accelerate a ship the size of a modern ocean liner to just half the speed of light, you would need a fuel tank containing more propellant mass than exists in our entire observable universe. It is not just impractical, it is a logical impossibility within our current understanding of physics. This is the tyranny of the rocket equation. It means that any spacecraft relying on internal fuel, on carrying its own reaction mass, is forever chained to this exponential curse. Chemical rockets, nuclear thermal engines, even the fabled antimatter drive, they all must obey this rule. They may change the efficiency, but they cannot escape the underlying mathematics of mass. This forces a complete paradigm shift in our thinking. If carrying fuel is a dead end for reaching the stars, then the only viable paths forward must fundamentally break this rule. A future craft cannot be a traditional rocket. It must either find a way to not carry its propellant at all, somehow pushing against something external, or it must discover a method to circumvent the need for reaction mass entirely. The rocket equation is not merely an engineering challenge, it is a cosmic signpost. It points away from bigger fuel tanks and toward more radical ideas, whispering that the secret to speed might not be in what we bring with us, but in how we learn to use the universe around us. Even empty space is not truly empty. Between the stars lies a sparse haze, a cosmic fog so thin we call it a near-perfect vacuum. In a typical cubic centimeter of this interstellar medium, you might find a single atom drifting in the profound quiet. For a car, a plane, or even our fastest current probes, this mist is utterly irrelevant, a ghost that offers no resistance. But for a ship approaching the speed of light, this ghost becomes a storm. At relativistic velocities, those lone atoms are no longer drifting specks. They transform into a relentless, high-energy barrage. Each impact strikes the hull with the force of a particle accelerator beam, slowly eroding the ship's surface and flooding the interior with dangerous secondary radiation. This is not friction in the traditional sense, but it acts like it, a drag imposed by the universe itself, sapping speed and integrity over a long journey. The intuitive solution, to simply add thicker armor, runs headlong into the tyranny of the rocket equation we just discussed. Every ton of shielding is mass that must be accelerated, requiring exponentially more fuel and making the entire endeavor less feasible. But the true danger is even more dramatic. Consider a speck of interstellar dust, a microscopic grain smaller than a grain of sand. At 90% of light speed, a collision with this tiny object would not be a simple puncture. The energy released would be cataclysmic, comparable to a substantial nuclear detonation right against the hull. One such encounter could vaporize an entire ship in an instant. This reveals a startling truth. The ultimate barrier to speed may not be a law of energy or time, but a problem of navigation. The galaxy is a shooting gallery, and at these velocities, every particle is a bullet. So how could we ever hope to travel safely? Future mission planners might have to chart courses through the galactic voids, the emptiest regions between the spiral arms, to minimize the risk. Or perhaps the ships themselves will need to generate immense forward-facing shields, not of physical armor, but of pure energy, using powerful lasers or magnetic fields to vaporize or deflect incoming hazards long before they strike. This environmental barrier forces us to see the cosmos not as a passive highway, but as an active participant in our journey. It resists our passage in subtle, material ways, reminding us that to travel among the stars, we must learn to read the map of the void itself. Beyond the dust and atoms lies a barrier woven into the fabric of reality itself. To see it, we must shrink our perspective down to the smallest conceivable scales, to a realm where the smooth, continuous spacetime of Einstein's equations begins to churn and boil. This is the domain of quantum foam. Imagine the placid surface of a pond, a perfect sheet representing the smooth universe we perceive. Now zoom in until you see the water's true nature, a seething dance of molecules constantly bubbling with fleeting energy. At the unimaginably tiny Planck scale, spacetime itself is theorized to behave this way, not as a serene stage, but as a turbulent, frothing sea of virtual particles popping in and out of existence. The universe at its most fundamental level may be granular. This hypothesis presents a startling possibility for our starship. As it accelerates to a significant fraction of light speed, it is not merely moving through empty space. It is plowing through this quantum foam. Each interaction with this seething granularity, each momentary tug from a virtual particle, could impose a form of quantum friction. It would be like trying to glide a hand perfectly smoothly through thick honey filled with countless tiny seeds, each creating a minuscule drag. The effect is unimaginably small at our human scales, utterly drowned out by other forces. But at relativistic velocities, these uncountable trillions of interactions could add up, creating a resistance born from the texture of reality. Some physicists speculate this could impose a final, ultimate speed limit, a fraction less than the speed of light itself. Even with a hypothetical engine of infinite power, you might find you simply cannot push through the foam any faster. The universe would have a maximum speed not because of energy, but because of texture. This idea sits at the thrilling and frustrating frontier of modern physics, where the colossal rules of general relativity collide with the probabilistic weirdness of quantum mechanics. We lack a complete theory to marry these two pillars, which means we cannot yet say for certain if quantum foam is real or what its effects truly are. But its potential existence serves as a profound reminder. Our quest to define the absolute speed limit may not end with the equations we know today. There may be layers to reality, deeper and more subtle, that we have only begun to glimpse. It encourages a humble curiosity, a recognition that the cosmos might guard its final secrets with principles we have not yet even learned to describe. Perhaps the only way to travel faster than light is to not travel at all, at least not in the conventional sense. What if, instead of fighting our way through the quantum foam and the interstellar haze, we could bring our destination to us? This is the radical promise of spacetime manipulation, a family of ideas that seeks to bend the very fabric of the cosmos to our will. The most famous of these is the Alcubierre warp drive, a concept born not from an engineer's blueprint, but from the mathematics of Einstein's own equations. Imagine a tiny bubble of normal space containing a spacecraft. Now, picture this bubble not moving through the surrounding universe, but instead, the universe itself moving around the bubble. The drive would work by contracting the fabric of spacetime tightly in front of the ship, pulling the destination closer, while simultaneously expanding spacetime behind it, pushing the point of departure farther away. The ship inside this warp bubble remains perfectly stationary within its own little pocket of reality. It experiences no acceleration forces, no time dilation, and crucially, it never locally exceeds the speed of light within its bubble. Yet the bubble itself, carried along by this engineered wave in spacetime, could theoretically cross interstellar distances at speeds far beyond light speed. It is not breaking the cosmic speed limit, it is cleverly rewriting the road. This idea transforms the problem from one of propulsion to one of geometry. We are no longer asking how to build a more powerful engine, but how to shape the stage upon which all motion occurs. It shifts the discussion from speed to control, suggesting that the ultimate mastery of travel is not about moving through the universe, but about learning to move the universe itself. Yet for all its elegant promise, the Alcubierre drive comes with a universe-sized catch. To create this compressive wave in front and expansive wave behind, the mathematics demands something extraordinary, exotic matter. This is not just rare or unusual material, it is a hypothetical substance that would possess negative energy density. In simple terms, it would have a gravitational effect opposite to normal matter. Instead of attracting, it would repel. It would be like a glue that pushes rather than pulls, necessary to hold the intricate shape of the warp bubble stable. The challenge is, no such substance is known to exist in nature, and many physicists believe it may be fundamentally impossible, potentially violating core quantum principles that govern how energy behaves at the smallest scales. The warp drive, therefore, exists in a fascinating limbo. It is mathematically permissible within the rules of general relativity, yet it may be physically forbidden by the deeper laws of quantum mechanics. It is a tantalizing signpost on the edge of known physics, pointing toward a realm of possibilities where travel is redefined not by velocity, but by the deliberate sculpting of reality's underlying structure. It asks us to consider that the final frontier might not be a place, but a skill, the skill of weaving spacetime itself. That cosmic shortcut through folded spacetime has a name, a wormhole. Picture the universe not as a vast, flat sheet, but as a piece of paper crumpled and folded. 2 points that lie far apart across the surface could be brought nearly touching by a tunnel punched straight through the higher dimensional bulk. This is the essence of a wormhole, a theoretical bridge connecting two distant regions of spacetime, offering a journey that could be, from the traveler's perspective, nearly instantaneous. It is a concept that emerges directly from the mathematics of Einstein's general relativity, not as a proven reality, but as a tantalizing possibility written into the equations that govern gravity itself. A spacecraft entering one mouth of a stable, traversable wormhole could emerge from the other, perhaps light years away, without ever having to accelerate to relativistic speeds. It would not be moving faster than light through space. It would be taking a shortcut that redefines what distance even means. The limit ceases to be about velocity and becomes about topology, the shape of the cosmos itself. This transforms interstellar travel from a marathon into a matter of finding the right door. Yet if the idea is elegant, the practicalities are daunting. The wormholes naturally predicted by relativity are not the stable cosmic subways of science fiction. They are incredibly unstable, prone to snapping shut in an instant, crushing anything inside. To hold one open, to make it traversable, theoretical models suggest you would need to line its throat with that same exotic, negative energy matter we encountered with the warp drive. This hypothetical substance would act as a kind of antigravitational scaffolding, propping the tunnel open against its own intense gravitational pull. The sheer amount of this exotic material and the energies required to create and manipulate it are so far beyond any technology we can conceive that the wormhole remains, for now, a profound thought experiment. But the challenges run even deeper than engineering. A stable wormhole that allows two-way travel opens a Pandora's box of causality paradoxes. If you can travel from point A to point B faster than a beam of light could travel the normal way, you could theoretically arrive back at your starting point before you even left. This creates scenarios where you could interact with your own past, leading to logical impossibilities that make physicists deeply skeptical about the true feasibility of such structures in our universe. So while wormholes captivate our imagination, they serve a crucial purpose in our understanding. They force us to think beyond linear journeys and raw speed. They ask us to consider the universe as a dynamic, malleable structure full of hidden connections and topological shortcuts. Their study, even as pure theory, stretches the boundaries of cosmology and inspires a fundamental shift in perspective. The ultimate limit to our voyages may not be how fast we can push our ships, but how deeply we can learn to read and navigate the folded geometry of reality itself. The most distant galaxies are not simply far away, they are slipping over a cosmic horizon, vanishing from our future forever. This is not a limit of engineering, but a consequence of the universe's own accelerating expansion, driven by the mysterious force we call dark energy. Think of the cosmos not as a static stage, but as an inflating balloon with galaxies like dots on its surface. As the balloon expands, the space between the dots stretches. For dots very close together, like the Milky Way and Andromeda, this expansion is negligible, overcome by their mutual gravitational pull. But for dots extremely far apart, the stretching of space between them adds up so dramatically that their separation increases faster than light itself could ever bridge the gap. This creates a cosmological event horizon, a boundary beyond which any light or signal emitted now will never reach us, and we will never reach it. Even a hypothetical spacecraft traveling at the absolute speed limit would be chasing a destination that is receding faster than it can pursue. The finish line is literally running away. For our most ambitious dreams, this imposes a sobering, absolute boundary. Our local group of galaxies, bound together by gravity, remains our island in the expanding ocean. Journeys to Andromeda, while monumentally difficult, remain within the realm of physical possibility. But the vast sea of galaxies beyond our local group, those stunning spirals and ellipticals we see in deep field images, are ultimately destined to become unreachable. They are sailing away on the current of spacetime itself, and we lack any paddle strong enough to catch them. This transforms our understanding of cosmic exploration from an open-ended adventure into a race against the universe's own clock. It means there is a finite window dictated by cosmology, during which certain distant destinations remain theoretically accessible. As eons pass, that window closes for more and more of the cosmos, isolating island universes from one another in a darkening, lonely expanse. This highlights a profound and humbling connection. The physics that governs the ultimate speed of our spacecraft is inextricably linked to the physics that governs the fate of the entire universe. Our travel capabilities are not just constrained by our engines or our courage, but by the fundamental dynamics of reality. It forces a poignant prioritization upon any future civilization. If we wish to reach beyond our galactic neighborhood, we must look to the stars not just with ambition, but with a deep understanding of the cosmic currents and a recognition that some voyages must begin before the universe itself closes the door. The universe itself may provide the fuel we so desperately lack. This is the elegant, almost poetic promise of the Bussard Ramjet, a starship designed not to carry its energy, but to harvest it from the void. Conceived in the 1960s by physicist Robert Bussard, the idea is breathtaking in its simplicity. Picture a craft not with tanks of volatile propellant, but with a forward-facing electromagnetic scoop, a net woven from magnetic fields thousands of kilometers wide. As the ship moves through space, this vast, invisible funnel would sweep up the sparse hydrogen atoms drifting in the interstellar medium, channeling them into a reactor at the ship's core. There, through a process of nuclear fusion, those captured atoms would be fused together, releasing a torrent of energy to create thrust, propelling the ship ever forward. It is a vision of a truly self-sustaining engine, a cosmic hunter that feeds on the thin breath of the galaxy to power its journey. In principle, it offers a brilliant escape from the tyranny of the rocket equation. Since the ship collects its fuel as it goes, it avoids the exponential penalty of carrying all that mass from the start. The faster it goes, the more hydrogen it rams into its scoop per second, potentially leading to even greater acceleration. In theory, such a craft could achieve a significant fraction of light speed, cruising across the interstellar ocean like a majestic sailing ship powered by the cosmic wind. Yet, as with all great ideas in astronautics, the devil is in the staggering details. The first major hurdle is the scoop itself. To collect enough of the incredibly diffuse interstellar hydrogen, the magnetic funnel would need to be truly enormous, spanning a cross-section larger than the planet Earth. Generating and maintaining fields of that scale is a challenge we cannot yet approach. Furthermore, this vast electromagnetic structure plowing through space would itself create a form of drag. The very act of collecting the fuel would slow the ship down, a parasitic loss that the fusion thrust must constantly overcome. This leads to the second, perhaps more fundamental problem, the fusion engine. The hydrogen collected from interstellar space is cold and incredibly thin. To fuse these atoms requires heating them to temperatures hotter than the core of our sun and compressing them to extraordinary densities. We struggle to achieve controlled fusion here on Earth with perfect, prepared fuel. Doing it reliably with a trickle of captured, deep space hydrogen is an engineering problem of a different magnitude altogether. And here lies the Ramjet's cruel catch-22. To collect enough hydrogen to even start the fusion process, the ship must already be traveling at a considerable speed, perhaps several % of light speed. But how does it reach that initial velocity without a conventional engine and its cursed fuel tanks? It may require a separate booster stage, bringing us right back to the initial mass problem the Ramjet was meant to solve. Furthermore, the feasibility of the entire concept depends heavily on the neighborhood. In the sparse regions between the spiral arms of our galaxy, the hydrogen is so scarce that even a perfect Ramjet might starve. It would only function efficiently in the denser clouds within the galactic arms, effectively charting a course along interstellar rivers of gas. So where does this leave the Bussard Ramjet? It stands as a masterpiece of creative engineering thinking, a bold attempt to turn a hindrance, the interstellar medium we once saw as a barrier, into a solution. It represents a crucial middle path in our thinking, a bridge between the known limits of conventional rocketry and the uncharted realms of spacetime manipulation. While its practical hurdles are immense, it teaches a vital lesson. Innovation in deep space travel may not be about building a more powerful engine in isolation, but about designing a ship that is an integral part of its environment, a craft that lives off the land, or rather the sky. It shows us that pushing the practical speed envelope might require us to stop seeing the universe as an empty highway and start seeing it as a landscape full of hidden resources, waiting for a clever enough traveler to use them. A sailboat does not carry the wind in its hold, it simply catches what the universe provides. This ancient wisdom finds its ultimate expression in a concept that turns light itself into a gale, the laser sail. Imagine not a rocket, but a vessel with a vast, mirror-thin sail, perhaps only a few atoms thick and kilometers across. Its engine is not on board at all, but anchored safely on Earth, or perhaps in orbit, a colossal array of lasers firing in perfect unison. Each photon striking that reflective sail carries a tiny, tiny bit of momentum. Individually, it is an imperceptible push, but trillions upon trillions of them, focused into a coherent beam of staggering power, can collectively exert a force. Over time, this gentle but unceasing pressure from pure light would accelerate the sail and its tiny attached probe to velocities once reserved for particles in an accelerator. This is photon propulsion, a way to move through space by surfing a beam. The beauty of this idea is its elegant escape from our oldest constraints. The spacecraft carries no fuel, no reactor, no volatile antimatter. It is, in its ideal form, just a sail and a payload. This completely sidesteps the crushing tyranny of the rocket equation. All the monstrous energy required for acceleration remains safely at home, powered by civilization's grid. The speed limit for such a craft is not set by infinite mass, but by practical physics, the power of our lasers and the strength of our materials. With a sufficiently powerful beam and a sail that can withstand the immense photon pressure without tearing or melting, theoretical models suggest small, gram-scale probes could be pushed to perhaps 20% of light speed. At that pace, a flyby of our nearest stellar neighbor, Proxima Centauri, could be achieved in just over 20 years, a blink in cosmic time. This is not distant speculation. It is the core mission of initiatives like Breakthrough Starshot, which aims to develop the technology to send a fleet of these tiny light sails to another star within a generation. They represent perhaps the most plausible near-term path to true interstellar exploration, a mission that could launch within the lifetimes of many people alive today. Yet for all its promise, laser sailing introduces a new set of profound and alien challenges. The infrastructure required is almost beyond comprehension. The laser array would need to be a coordinated network with a total power output rivaling that of entire nations, focused with atom-scale precision on a sail the size of a city as it recedes into the interstellar dark. The targeting alone is a nightmare of celestial mechanics, requiring us to aim not at where the probe is, but where it will be years after the light from our lasers finally reaches it. And then there is the most sobering limit of all, the problem of stopping. A laser sail is a one-way ticket. The beam from home can push, but it cannot pull. Once the probe reaches its target star, how does it slow down to make observations? It would scream past at a fifth of light speed, its encounter lasting mere hours. Some concepts suggest using the star's own light pressure or a magnetic field from the star to slow a second, smaller sail, but the engineering becomes exponentially more complex. So laser sailing offers a thrilling yet narrow window. It is a method perfectly suited for small, rugged, disposable scouts, our first robotic eyes on another star system. It trades the dream of human journeys for the pragmatic goal of pure knowledge, proving that we can reach the stars not by building a faster engine, but by building a brighter lamp. It demonstrates that the key to breaking one speed barrier may lie in rethinking the very source of our motion, harnessing external energy on a cosmic scale. That sail is pushed by light, but what if we could harness the very essence of matter's destruction? Deep within the heart of physics lies a reaction of perfect, terrifying efficiency. When a particle of matter meets its exact opposite, its antimatter counterpart, they do not merely combine or explode, they vanish. In a flash of pure energy, 100% of their combined mass is converted according to Einstein's famous equation. Energy equals mass times the speed of light squared. This annihilation is the most energy-dense process we know of in the universe, the ultimate fuel. In theory, an antimatter engine could use this torrent of energy, channeling it into a focused exhaust to propel a starship to speeds far beyond anything chemical or nuclear engines could ever achieve. It represents the absolute pinnacle of reaction-based propulsion, the final word in raw power. The dream is compelling. A tiny droplet of this exotic fuel containing the energy of a mountain of conventional rocket propellant. But this dream is guarded by challenges that are equally absolute. The first and most fundamental is simply making the fuel. Antimatter does not exist naturally in any usable quantities. We must create it particle by precious particle in massive particle accelerators like the Large Hadron Collider. The current global production rate is measured in billionths of a gram per year at a cost that would make the most extravagant diamond look like gravel. To fuel a single interstellar mission, we would need to scale up production by a factor of many billions, a feat requiring energy infrastructures that dwarf our entire planetary civilization. And then you must store it. Since antimatter annihilates upon contact with any normal container, it must be held in perfect isolation within magnetic or electric fields in a state called a penning trap. Any power failure, any microscopic flaw, and the entire fuel supply would instantly react with the walls of its container in a catastrophic release of energy. The engineering required is a nightmare of precision and reliability. Even if we miraculously solved production and storage, the engine itself presents a radiation problem of cosmic proportions. Primary product of matter-antimatter annihilation is an intense burst of high-energy gamma rays. This is not simple heat or light. It is penetrating radiation that would fry any onboard electronics and crew. Shielding against such a torrent would require immense amounts of mass, once again invoking the tyranny of the rocket equation we sought to escape. And here we encounter the cruelest reminder of all. Even with this perfect fuel, the relativistic walls still stand. As the ship approaches light speed, its mass still increases, demanding ever more energy for each incremental gain. The antimatter engine may give us a far more powerful torch, but it does not erase the fundamental curve of spacetime that makes the final ascent to light speed infinitely steep. So antimatter propulsion occupies a strange and poignant place in our quest. It is the brightest torch, the most potent key we can conceive of within the known laws of physics. It shows us the theoretical peak of what is possible if we master the universe's most volatile substances. Yet it also highlights with stark clarity that raw power alone may not be the final answer. It forces us to ask whether the ultimate engine for crossing the stars will be found in harnessing destruction, or in discovering something far more subtle, a way to move without fighting the universe's deepest rules at all. The ultimate engine may not burn fuel at all, but instead feed on the slow evaporation of a captive star. This is the startling premise of the Kugelblitz drive, a concept that sounds like pure science fiction, yet is rooted in the strange marriage of quantum mechanics and gravity. The name comes from the German word for ball lightning, but the reality it describes is far more exotic. Imagine focusing not lasers, but an unimaginable concentration of pure energy into a region of space smaller than an atom. According to Einstein's equations, energy warps spacetime, and enough of it, concentrated to a critical density, could theoretically collapse into a microscopic black hole. This would not be a black hole born from a dying star, but one forged from light itself, a Kugelblitz. The propulsion idea hinges on a famous prediction by Stephen Hawking. Quantum effects near a black hole's event horizon cause it to slowly leak radiation, a faint glow of particles that carries away the black hole's mass. For a large astrophysical black hole, this Hawking radiation is utterly negligible, far too weak to ever be detected against the cosmic background. But for a microscopic black hole, the story is completely different. The smaller the black hole, the faster it evaporates, radiating away its mass in a torrent of high-energy particles. A black hole with the mass of a small mountain would glow with the intensity of 1 million nuclear power plants, and it would do so for years. A Kugelblitz drive would seek to create and then carefully feed such an object, using its furious Hawking radiation as a perfectly efficient exhaust. The ship would, in essence, ride the gentle but relentless push of a dying artificial star. The theoretical appeal is immense. The specific impulse, a measure of propulsion efficiency, would be astronomically high, potentially allowing for sustained acceleration to a significant fraction of light speed without the need to carry mountains of reactive mass. It represents a power source of almost mythical density, turning the most destructive phenomenon in the cosmos into a controlled furnace. Yet the challenges are so profound they border on the philosophical. First, creating the black hole. The energy required is far beyond anything our species can muster, equivalent to focusing the entire output of our sun for years into a point smaller than a proton. The engineering to achieve such a concentration is not just beyond us, it is a feat that redefines the scale of megaprojects. Second, and more critically, is control. How do you feed a microscopic black hole just enough to keep it from evaporating completely without letting it grow uncontrollably? How do you contain something that, by its very nature, consumes everything it touches? The magnetic and gravitational systems needed to hold this pinpoint singularity in perfect suspension at the heart of a starship are purely speculative. Any failure would be instantly catastrophic. Furthermore, harnessing the Hawking radiation itself is a nightmare of physics. This radiation is not a clean, directional exhaust like a rocket plume. It is a spray of particles and gamma rays in all directions. Turning that isotropic blast into usable thrust would require a kind of asymmetric shield or reflector we have no idea how to build. So while the Kugelblitz drive is a breathtaking exercise in theoretical physics, it serves a purpose greater than a blueprint. It illustrates the extreme directions thought must travel when confronting the energy limits of the cosmos. When chemical, nuclear, and even antimatter fuels seem insufficient, we are pushed to consider manipulating spacetime and quantum gravity themselves. This drive symbolizes the audacious human desire to tame the universe's most violent processes, not for destruction, but for the peaceful purpose of crossing the interstellar ocean. It stands as a testament to ingenuity in the face of absolute constraints, a reminder that the final answer to our journey might not lie in a better fuel, but in learning to build and ride a star of our own making. The void may not be empty, but alive with a hidden energy we could learn to push against. This is the radical proposition of the quantum vacuum thruster, a concept that asks us to see the nothingness between stars not as a barrier, but as a potential propellant. At the quantum level, what we call empty space is a seething sea of activity. Pairs of virtual particles, matter and antimatter, constantly wink into existence for the briefest moment before annihilating each other, a temporary loan of energy from the universe that is almost instantly repaid. Some theoretical models suggest a cleverly designed cavity, shaped with precise electromagnetic fields, could create an imbalance in this quantum foam. More virtual particles would appear and push on one wall of the chamber than the other, generating a tiny net force. This would be a true reactionless drive, a device that moves forward by pushing against the very fabric of spacetime, with no exhaust and no onboard fuel to carry. The implications are staggering. A ship equipped with such an engine could, in theory, accelerate continuously. It would not need to carry reaction mass, completely sidestepping the rocket equation. Over months or years of constant, gentle thrust, it could build up to tremendous speeds, a slow and steady push that eventually wins the interstellar race. This promise has fueled controversial experiments, most famously a device called the M-Drive. Its inventors claimed to measure a small but persistent thrust from microwaves bouncing inside a sealed, asymmetrical chamber, a result that seemed to defy the classical conservation of momentum. If the thrust was real, where was the equal and opposite reaction? The scientific community responded with intense skepticism. Repeated tests by independent teams have failed to consistently reproduce the effect, often finding that the tiny measured forces could be explained by experimental errors, thermal expansion, or subtle magnetic interactions with the Earth's field. The central criticism is fundamental. A device that produces thrust without expelling anything appears to break one of physics' most cherished laws. For such a drive to be valid, it must be exchanging momentum with something. The only candidate is the quantum vacuum itself, suggesting the vacuum is not just a backdrop, but a medium with properties we can interact with. This places the idea on the very fringe of established physics, caught between revolutionary potential and the rigorous demand for proof. It highlights a beautiful tension in our quest to understand the cosmos. On one hand, we must be fiercely loyal to the laws that have been tested and proven for centuries. On the other, we must remain open to the possibility that our understanding of those laws is incomplete, especially in realms we have barely probed. The quantum vacuum thruster, whether it ultimately works or not, serves a vital purpose. It forces us to look deeper at the nature of nothing. It asks if the ultimate engine for our journey might not be something we bring, but something we learn to borrow from the universe's own hidden, restless substrate. It is a reminder that the final frontier of speed may be discovered not by building a bigger rocket, but by learning to have a conversation with the silent, seething dark. The universe itself begins to warp before the ship's prow. At a significant fraction of light speed, the simple act of looking forward becomes a disorienting exercise in relativistic physics. The stars ahead do not just twinkle, they crowd together, piling up in a brilliant, tunnel-like band directly in front of the ship due to an effect called relativistic aberration. Meanwhile, the light from those stars is violently blue-shifted, their colors crammed into a narrow, harsh spectrum of high-energy ultraviolet and even X-rays. The familiar constellations smear and collapse into a single, blinding headlight, while the cosmos behind reddens into a dim, infrared void. This is not a visual glitch. It is the universe as it truly appears when you're moving through it fast enough to bend the very paths of light. For a human navigator, this view would be useless, a psychedelic distortion offering no reliable map. It means that traditional star charts and even GPS-like systems based on known pulsar signals would require constant, complex recalibration in real time. The ship's computer must untangle this distorted sky, using the precise frequencies and positions of the blue-shifted stars to calculate its true trajectory, all while barreling through the void at a pace where a 1-degree error could mean missing a target star by trillions of kilometers. This computational burden is relentless, a constant high-stakes puzzle where the pieces are constantly changing shape, and there is no one back home who can help. At these speeds, the delay in communication with Earth stretches from minutes to years. A simple query for course verification, sent from a ship halfway to Alpha Centauri, would take over 2 years to reach mission control, and the reply another 2 years to return. By the time the answer arrives, the ship would have traveled light years further, its original question rendered irrelevant by countless new navigational hazards. This forces a complete paradigm of autonomy. The onboard artificial intelligence ceases to be a tool and becomes the mission's silent captain. It must process a flood of sensor data from the distorted sky, the tenuous interstellar medium, and long-range hazard scans. It must identify a rogue planetesimal, a dense pocket of gas, or a micrometeoroid swarm not on any chart, and it must compute an evasive maneuver in milliseconds, because at 0.99 light speed, you are covering over 290,000 kilometers in the blink of an eye. There is no time for deliberation, only for flawless, pre-programmed instinct augmented by adaptive learning. The AI's decision loop, the time it takes to sense, analyze, and act, becomes a critical performance metric as fundamental as engine thrust. If the ship's velocity outpaces its processor's ability to react, the mission ends in a silent, instantaneous flash. This introduces a subtle but profound physical limit. The very act of computation has an energy cost and generates heat. As the AI works harder, processing more data at faster rates to keep up with the ship's velocity, its power demands and thermal output soar. On a decades-long voyage, managing this waste heat becomes a critical engineering challenge, as there is no cold of space to dump it into when your hull is already glowing from interstellar particle impacts. Furthermore, as we push computing to its ultimate limits, we may encounter a barrier not of software but of physics. At extremely small scales, quantum effects like tunneling can cause errors in classical computer chips. Building a computer reliable enough to guide a starship for a century, while potentially needing to leverage quantum principles itself for unprecedented processing power, is a challenge that sits at the crossroads of computer science and fundamental physics. The journey's success, therefore, hinges on a delicate, integrated dance. The propulsion system defines the possible speed, but the computational mind defines the safe speed. It is a reminder that the vessel we send will not be a simple hull with an engine. It must be a unified organism where advances in spacetime physics and silicon intelligence evolve together, each pushing the other toward a common, distant point in the dark. That computational mind must command a vessel of almost mythical resilience. The hull of a relativistic starship is not a passive shell. It is the primary interface with a universe turned hostile. Traveling at even half the speed of light transforms the thin mist between stars into a relentless, high-energy sandblaster. Each individual hydrogen atom, harmless at everyday speeds, strikes the leading edge with the fury of a particle accelerator beam. This constant barrage does two devastating things. First, it transfers immense kinetic energy directly into the hull's atoms, heating the surface to temperatures that can exceed the core of our Sun. Second, these high-velocity impacts cause physical erosion, slowly but surely blasting molecules away from the surface, atom by atom. Over a decades-long journey, this could sand away critical layers of shielding or sensors. But the true terror comes from anything larger than a lone atom. A mote of dust, a microscopic grain smaller than a grain of sand, would strike with the energy of a ton of conventional explosive. A pebble-sized object would deliver a cataclysm comparable to the atomic weapon used at Hiroshima, focused on a single point. The hull must therefore be more than heat-resistant. It must be virtually indestructible, capable of absorbing or deflecting impacts that carry the punch of nuclear blasts. This forces material science into realms we can barely conceive. We are not talking about better steel or advanced ceramics. We are talking about engineering the very architecture of matter itself. One promising frontier lies in metamaterials, substances engineered at the nanoscale to have properties not found in nature. Imagine a hull woven from carbon nanotubes or sheets of graphene, a single layer of carbon atoms arranged in a hexagonal lattice. These structures boast tensile strengths hundreds of times greater than steel while remaining incredibly light. But strength alone is not enough. The material must also be an incredible conductor of heat, spreading the immense thermal load across the entire structure to prevent any single spot from melting. It might need embedded capillaries of liquid coolant that circulate and radiate heat away from the leading edges. Even more fantastically, it may need to be self-healing. Inspired by biological systems, future hull composites could contain reservoirs of liquid monomer. When a microscopic crack forms from an impact, this liquid would wick into the breach and polymerize, solidifying to seal the wound automatically. Some concepts go further, suggesting hulls built from diamondoid structures, where every atom is precisely placed in a rigid, diamond-like lattice, offering unparalleled strength and thermal conductivity. Yet for all their promise, these are laboratory dreams. We currently produce graphene in patches the size of postage stamps, not in the square kilometers needed to sheath a starship. The manufacturing techniques to assemble atomically perfect diamondoid materials on a macroscopic scale simply do not exist. We are likely many decades, if not centuries, away from such technology. This creates a profound bottleneck. You can design the perfect engine, the flawless navigation system, but if you lack a hull that can survive the journey, the mission is stillborn. The material limit is the ultimate practical gatekeeper, a sobering reminder that interstellar travel is not a single breakthrough but a symphony of them. The quest for ultimate speed is in equal measure a quest for the ultimate armor, a silent demand that we learn to build not just faster ships, but tougher ones, forged from the future's periodic table. Even the most perfect ship is a prison without a crew that can survive the journey. Our bodies, evolved for the gentle conditions of Earth, face a gauntlet of invisible threats the moment we leave our planet's protective cradle. The first and most pervasive is microgravity. Floating may seem like freedom, but for our biology, it is a slow unraveling. Without the constant pull of gravity to work against, muscles atrophy, bones lose density at a rate of about 1% per month, and the heart, no longer fighting gravity to pump blood upward, weakens. On a voyage lasting decades, even with rigorous daily exercise regimens, a crew could arrive at their destination too frail to stand under alien gravity, their skeletons brittle as old chalk. Compounding this is the silent, relentless rain of cosmic radiation. Here in Earth's magnetic bubble, we are largely shielded from the high-energy particles that sleet through interstellar space. But a ship traveling between stars is exposed to a continuous background drizzle of galactic cosmic rays, punctuated by sudden, violent storms from distant supernova. This radiation does not just increase cancer risk, it can cause cumulative damage to the brain and central nervous system, potentially leading to cognitive decline over the long term. Shielding against it requires mass, often water or specialized materials, which once again collides with the rocket equation, forcing a terrible trade-off between protection and the ability to get there at all. These are not hypothetical concerns, they are the daily reality aboard the International Space Station, magnified over a timescale of generations. They form a biological speed limit, a threshold defined not by engine power, but by the human body's slow decay in an environment it was never meant to inhabit. Yet the greatest challenges may not be physical but existential. Consider a crew embarking on a mission to a star 100 light-years away. Thanks to time dilation, their journey might take only 20 years of their own lived experience. But when they return, triumphant with their discoveries, they step back onto an Earth where over 200 years have passed. The society that launched them with its culture, its politics, its very language is gone, preserved only in archives. Their families, friends, everyone they ever loved have passed on. They are pioneers in the most absolute sense, cut adrift from their own history. This raises profound ethical questions. What is the purpose of a mission if its explorers can never truly come home to share what they have learned? Are we sending them on a voyage of discovery or into a form of permanent exile? The crew becomes a living time capsule, a relic of a past era struggling to find meaning in a future that has moved on without them. The psychological weight of this knowledge, carried every day of the flight, is immense. It transforms the mission from a grand adventure into a sacrifice, a willing severing from one's own timeline for the sake of knowledge alone. Confinement compounds this temporal isolation. Imagine spending decades inside a sealed, humming environment, with the same small group of people, the same recycled air, the same relentless view of the star tunnel ahead. The social dynamics become a critical life support system. Personality conflicts that might be minor on Earth can fester and erupt in the pressure cooker of a starship, where there is no escape, no change of scenery, no new faces. The monotony and sensory deprivation alone could erode mental health, leading to depression, anxiety, or irrational decision-making. The ship's artificial intelligence might manage the engines and navigation, but it cannot mediate a human heart or soothe a profound, cosmic loneliness. This psychological frontier may be the most unpredictable and dangerous of all, for it resides not in metal or physics, but in the human mind itself. Faced with these converging limits of flesh, time, and psyche, our very concept of a crew must evolve. One path is to remove the human element from the immediate journey altogether. Robotic probes like the laser-sailed scouts we discussed could be our first true interstellar ambassadors, unburdened by life support, radiation shielding, or the need for a return trip. They can be optimized for one purpose: speed and data collection. They represent the purest form of exploration, where the mission's success is measured in bits of information radioed back across the light years. For human travel to follow, we may need to suspend our biological selves entirely. Suspended animation, or cryogenic stasis, is a staple of science fiction for a reason. By drastically lowering the body's metabolic rate, we could theoretically put a crew into a dreamless sleep for centuries, bypassing the psychological toll of the journey and the need for generational ships. But the medical hurdles are staggering, preventing tissue damage from ice crystals and ensuring safe revival are problems we are nowhere near solving. An even more radical proposal is to send not our bodies but our minds. The concept of digital consciousness transfer, uploading a neural pattern into a robust computational substrate, is the stuff of distant philosophical speculation. Yet it hints at a future where the vessel and the voyager become one. An uploaded crew would be immune to radiation, aging, and confinement, potentially able to experience the voyage subjectively over millennia or in a compressed instant. But this raises its own profound ethical quandaries about identity, consciousness, and what it truly means to be human. It suggests the ultimate spacecraft might not carry people at all, but something new, something born from our minds but freed from our biological chains. Therefore, the absolute speed of a future spacecraft is not a single number on an engineer's spreadsheet. It is a complex equation where the physical limits of light and energy are multiplied by the biological limits of bone and brain and divided by the ethical weight of time and sacrifice. The fastest possible ship may be one that carries no fragile, breathing humans at all, or it may be a ship that carries us in a form we cannot yet imagine, on a journey that redefines not just where we can go, but what we are when we get there. The ship's mind must be as resilient as its hull. While we design materials to withstand the storm of relativistic travel, we must also forge an intelligence capable of steering through it. This is where artificial intelligence transitions from a helpful tool to an indispensable partner, a co-pilot for a journey where human reaction times are meaningless and the margin for error is zero. Artificial intelligence would not merely assist the mission, it would become the mission's enduring consciousness, managing systems whose complexity would overwhelm any human crew. Think of the Starship not as a vessel with a computer, but as a computational entity that happens to have engines and sensors. Its artificial mind would perform a symphony of tasks simultaneously. It would monitor the structural integrity of that diamondoid hull, analyzing stress patterns from a billion micro-impacts and initiating self-repair protocols before a human eye could even notice a flaw. It would manage the colossal energy flows of a fusion or antimatter reactor, making micro-adjustments millions of times per second to maintain perfect efficiency and stability. In a laser sailcraft, where a course correction requires tilting a sail the size of a city by a fraction of a degree from light years away, the artificial intelligence would be the only entity capable of the calculation. It would analyze the Doppler-shifted starlight, account for the pressure of the interstellar medium on the sail, and fire its own tiny attitude thrusters with a precision that borders on clairvoyance, all without a single instruction from Earth. This is because at such distances, waiting for a command from mission control is impossible. The round-trip communication delay could be decades. The ship must think for itself. It must be autonomous. This autonomy reaches its peak in hazard navigation. Machine learning algorithms, trained on vast simulations of interstellar space, would constantly scan the forward vista. They would not just look for known dangers, but learn to predict new ones, identifying the faint signature of a dust cloud too diffuse for pre-programmed sensors, or calculating the probabilistic path of a rogue asteroid. The artificial intelligence would then devise and execute evasive maneuvers in real time, trajectories that minimize drag and energy expenditure while maximizing safety. It would do this not by following a rigid list of rules, but by adapting, learning from each near miss and each scan of the void, becoming a better navigator with every light year traveled. This adaptive learning is key to pushing the practical speed limit. An engine's theoretical maximum is one thing, its real-world performance under fluctuating conditions is another. An artificial intelligence could continuously optimize engine output, balancing thrust against fuel consumption and thermal load, perhaps discovering more efficient firing patterns that human engineers never conceived. It turns the spacecraft from a static machine into a living, learning system that grows more capable the longer it flies. In this way, artificial intelligence does not change the absolute speed of light, but it dramatically extends the practical speed at which we can safely and reliably travel. It raises the ceiling of what is feasible by mastering the countless variables that would otherwise ground a starship or doom it to failure. The synergy between artificial intelligence and spacecraft engineering marks a fundamental paradigm shift. The limits of interstellar travel are no longer purely physical constraints of energy and mass. They are also computational limits of data processing, pattern recognition, and decision-making speed. The vessel that finally reaches another star may be commanded not by a human captain gazing at the viewscreen, but by a silent, relentless intelligence born from our own. Its processors, cool and flawless, would hold the mission's purpose across centuries, making it the true explorer of the high-speed frontier. The story of our journey to the stars is, therefore, being written in two languages, the language of cosmic constants and the language of code. The most powerful engine ever conceived is useless without a civilization capable of building its launch pad. The economic and logistical scale of a relativistic starship project transcends anything in human history, moving from national budgets to planetary ones. We are not talking about a single rocket on a pad, but an entire industrial ecosystem in space. Consider the infrastructure for a simple laser sail mission. The beamer array, a network of coordinated lasers with the combined output of a global power grid, would itself be an orbital megastructure. Its construction would require mining asteroids for materials, assembling vast mirrors in zero gravity, and creating power sources, perhaps vast solar farms spanning thousands of kilometers, all before a single gram of the sail probe is built. The project would demand a sustained, multi-generational effort, a century-long endeavor where the architects would never live to see the launch, and their grandchildren would witness only the beginning of the probe's multi-decade flight. The cost in resources, energy, and human focus is almost incalculable within our current economic frameworks. It would require a level of global coordination and shared purpose that has eluded our species throughout its history, a shift from competing national interests to a unified, species-level project. This societal limit may prove as binding as any law of physics. Can we muster the collective will to build something whose primary benefit lies centuries in the future? The endeavor presupposes a stable, patient civilization, one that has moved beyond scarcity and short-term thinking. It suggests that the speed of our future craft is inextricably tied to the maturity of our social and economic systems. We must evolve not just technologically, but as a cooperative global community, learning to steward resources and sustain vision across generations. The launch complex for an interstellar voyage, therefore, is not a facility on Earth, but the civilization that builds it. Perhaps the greatest shortcuts are those the universe has already built. Beyond our blueprints and equations lies a tantalizing possibility that deep space itself might be threaded with natural fast lanes, cosmic currents that could carry a ship farther and faster than its engines alone ever could. This is not about breaking the laws of physics, but about finding where those laws are bent by the cosmos's own architecture. Some speculative theories point to the intricate webs of magnetic fields that stretch between galaxies, vast rivers of force woven by stellar winds and supernova remnants. A vessel equipped to ride these field lines like a surfer catching a perfect wave might harness their energy for acceleration or guidance, reducing its own fuel burden dramatically. Other concepts delve into the exotic geometry of spacetime itself. Could there be regions where the fabric of the cosmos is naturally thinner, or where gravitational waves from ancient collisions have left lingering corridors of distorted space? In such a place, the same amount of thrust might yield a greater effective velocity, a subtle tailwind from the universe's own history. While no such phenomena have been confirmed, the search for them transforms deep space astronomy from a passive act of observation into an active hunt for cosmic anomalies. Telescopes scan not just for stars and planets, but for irregularities in the cosmic microwave background, for unexplained velocity dispersions in star clusters, or for strange lensing effects that could hint at hidden structures. It encourages a profound openness to serendipitous discovery, the chance that our most powerful instruments might one day reveal a shimmering path in the data, a signature of a road not on any of our charts. If such pathways exist, they would utterly redefine the practical speed limits for any craft clever enough to find them. Navigation would become less like plotting a course across an ocean and more like a cosmic treasure hunt, deciphering ancient stellar maps and gravitational clues to locate the hidden on-ramps to the interstellar highway. The ship's most important instrument might not be its engine, but its suite of sensors constantly tasting the solar wind, mapping magnetic fields, and probing the local curvature of space for any sign of a favorable current. This possibility serves as a humbling and thrilling reminder. Our three-dimensional maps of star positions are still just the surface layer of a far deeper cosmic topography. The ultimate speed for a future spacecraft may depend less on the power we can generate and more on the subtle geography we can learn to read. It suggests that the final frontier of travel is not merely a challenge of engineering, but one of perception, waiting for explorers with the patience to listen to the universe's quiet whispers and the courage to sail into its uncharted flows. But what if the ultimate speed limit is not universal, but merely local? Our entire discussion has been framed by the physics of this single cosmos, the constants and laws we have painstakingly measured. Yet some of the most profound theories in modern cosmology suggest our universe may be just one page in an infinite book, a single bubble in a frothing sea of creation known as the multiverse. In this staggering view, each universe could have its own unique set of physical laws, its own value for the speed of light, its own strength of gravity. In a cosmos next door, light might travel 1,000,000 times faster, or space itself might be folded into more than 3 dimensions we experience. This is not idle speculation, but a serious consequence of theories like eternal inflation and string theory, which attempt to explain the fundamental nature of reality. If such a multiverse exists, it presents a mind-bending possibility. The absolute speed limit for a spacecraft might not be a fixed rule, but a variable condition, something that depends entirely on which universe you are in. The challenge then shifts from pushing against our local laws to finding a way to step outside them entirely. This is the realm of dimensional travel, a concept that sounds like pure fantasy, but emerges from the mathematics of advanced physics. Our reality appears to have 3 spatial dimensions: length, width, and height. But to make their equations work, theories like string theory require more, perhaps 10 or 11 dimensions total. These extra dimensions are thought to be curled up at scales far smaller than an atom, invisible to us, but fundamentally part of the fabric of everything. Some models, like brain-world cosmology, propose that our entire universe is a three-dimensional membrane, or brain, floating within a higher dimensional space. In this view, the force of gravity, which seems so weak compared to other forces, might actually be strong, but its influence is diluted because it leaks into these extra dimensions. This leakage could theoretically be exploited. A craft that could somehow manipulate or anchor itself in a higher dimension might bypass the normal constraints of three-dimensional space, achieving effective motion that appears superluminal from our limited perspective. It would be like an ant walking across a folded piece of paper. To another ant confined to the paper's surface, the journey is long. But if the ant could briefly step off the surface into the third dimension, it could reappear instantly on the other side of the fold. For a starship, this would not be about speed, but about access, finding a door out of the flatland of our perception. Concepts like traversable wormholes, which we discussed earlier, can be seen as manifestations of this dimensional thinking, tunnels through the higher dimensional bulk. While these ideas remain firmly in the domain of theoretical physics, with no experimental evidence and monumental technological hurdles, their value is not in providing a blueprint. It is in the perspective they force upon us. They challenge the very notion of an absolute limit by suggesting that limits are contextual. The rules that bind us here might be mere bylaws in a single cosmic township. The dream of a future craft, therefore, expands from a vehicle that moves through space to one that might learn to navigate the meta-geography of reality itself. A vessel capable of changing the playing field rather than just playing the game better. This fuels the furthest reaches of scientific imagination, inspiring a long-term perspective where our current physics is not the final word, but a first chapter. It asks us to consider that the true frontier of speed may lie not in reaching the horizon of our universe, but in discovering a way to step beyond its walls entirely. Our drive for speed is more than a technical challenge. It is a mirror reflecting our deepest human questions. As we push against these myriad physical limits, from the quantum foam to the tyranny of the rocket equation, we must pause and ask a more fundamental question. Why do we feel this compulsion to reach such impossible velocities, to risk so much for the distant glimmer of another star? The answer is not found in an equation, but in our purpose. The goal of the journey may ultimately define the necessary speed, rather than the other way around. Consider the different missions we might undertake. If our purpose is pure exploration, to send our first robotic eyes to another star system, then moderate fractions of light speed are not just acceptable, they are revolutionary. A probe traveling at 20% of light speed, like a laser-sailed scout, could reach our nearest stellar neighbor in a human lifetime and radio back its findings. This mission values knowledge above all else, and its speed requirement is defined by the patience of the civilization that sends it. The philosophical limit here is one of curiosity, a desire to see what lies in the cosmic backyard. But what if our purpose shifts from exploration to preservation? If the goal is to ensure the long-term survival of humanity, to carry the essence of our civilization beyond any single star, then the speed requirement changes dramatically. A generational ship traveling at 1% of light speed might preserve a living community, but it would take tens of thousands of years to reach another habitable world. In that time, the society inside the ship could evolve into something unrecognizable or face collapse. For a true preservation mission, to plant a seed of humanity in another galaxy within a meaningful time frame, circumventing the light speed limit becomes not just desirable but imperative. The philosophical driver shifts from curiosity to legacy, from observation to continuation. This purpose demands we invest our ingenuity in the most radical ideas, from warp drives to dimensional shortcuts, because the stakes are the survival of a species. And what of connection? If our purpose is to build a true interstellar community, to trade and communicate and share cultures across the light years. Then the speed of information and travel defines the texture of that society. A network connected by ships traveling at half of light speed is still a network of isolated islands, where a simple conversation could take decades between replies. This would create a civilization of profound patience, or perhaps profound loneliness. To forge a connected galactic culture, we would need to achieve something close to instantaneous travel or communication, bending the laws of physics to serve our social nature. Here, the philosophical limit is about kinship, a refusal to be alone in the dark. This interplay between purpose and possibility forces a crucial introspection. It reminds us that technology is never neutral. It is a tool that serves human ends. The quest for ultimate speed is at its heart a quest for meaning. Are we seeking to understand the universe, to save ourselves within it, or to find company among its stars? Each answer points to a different engineering path, a different allocation of a civilization's resources and spirit. Our relentless drive to go faster, then, is not merely a competition against cosmic constants. It is an expression of our curiosity, our fear of extinction, and our longing for connection. It is the sound of a young species standing on the shore of a cosmic ocean, deciding what kind of swimmers it wants to be. The final limit may not be written in the fabric of spacetime, but in the values we choose to carry with us as we learn to read it. Mapping this journey requires a timeline not of years, but of human ambition itself. We can chart a plausible roadmap to the stars, a sequence of technological eras defined not by the limits we face, but by our capacity to transcend them. The first era, unfolding within the next century, belongs to the Scouts. This is the domain of light sails and advanced nuclear propulsion, where our ambition is focused not on human passengers, but on sending our senses ahead. Small, rugged probes, perhaps no larger than a smartphone, could be pushed to 10 or even 20% of light speed by vast laser arrays. These are not the majestic starships of legend, but intelligent cameras and sensors, our first robotic fingertips reaching out to touch another star. Their mission is pure discovery, to beam back a single, priceless postcard from a world orbiting Proxima Centauri, proving that the voyage itself is possible. Success here would be a psychological and scientific earthquake, transforming interstellar travel from a dream into a documented engineering feat. It would teach us how to navigate the relativistic void, manage communications across light years, and harden machinery against the interstellar environment. This near-term horizon is tantalizingly close, a project that could see its first launch within the lifetime of many watching today. It is a necessary, humble first step, proving we can reach another sun before we dare to send a human heart to beat under its light. Building on that foundation, the midterm era, perhaps spanning the next few centuries, shifts the goal from observation to visitation. This is where the staggering challenges of human survival in deep space must be met. Breakthroughs in contained fusion, or the first tentative harnessing of antimatter, could provide the sustained, colossal power needed for vessels large enough to sustain a crew. These would not be ships of leisure, but arcs of immense complexity, carrying closed ecosystems, artificial gravity, and shielding measured in meters thick. Their target speed might still be in the range of 10 to 20% of light speed, a pace that makes journeys to nearby stars' missions lasting decades or even a century of ship time. This era solves the propulsion puzzle at a human scale, but it fully confronts the biological and psychological limits we discussed. It demands we master suspended animation, or learn to build societies that can thrive in permanent isolation, where the crew that arrives are the distant descendants of those who departed. This timeline depends not just on physics, but on our societal stability, requiring a civilization patient enough to plant trees under whose shade it will never sit. It is the era of great arcs, a testament to endurance over speed. The far term, stretching over millennia, is the realm of fundamental physics. Here, we move beyond pushing matter through space and begin to ask how to move space itself. This era is conditional, hinging on discoveries we have not yet made. It is the domain of spacetime manipulation, where concepts like the warp drive or stable wormholes transition from mathematical curiosities into engineering principles. It might involve harnessing phenomena we currently label as quantum gravity effects, learning to interact with the universe on a level where our current distinctions between energy, matter, and dimension blur. In this distant future, the notion of speed percentage becomes almost quaint. Success here would mean redefining distance, making a journey across the galaxy a matter of topology and control rather than velocity and time. This timeline is not a prediction but a possibility, a branch on the tree of progress that only grows if we continue to invest in pure, curiosity-driven science for generations. It represents the ultimate technological ascent, where we don't just build better ships but learn to read the deeper blueprints of reality. This entire roadmap, however, is drawn on shifting sand. Its contours are not dictated by immutable laws of physics alone, but by the fragile, human laws of economics and priority. A sustained global commitment to basic science could accelerate breakthroughs in fusion or materials, compressing the timeline. Conversely, a turn inward, a focus on terrestrial conflicts or short-term crises, could stall our progress for centuries. The greatest variable is the unforeseen discovery, the serendipitous experiment that reveals a new principle, rendering our careful projections obsolete overnight. The timeline, therefore, is not a schedule, it is a vision. It structures our hope, showing that each daunting limit, from the rocket equation to cosmic radiation, is not a stop sign but a milestone. Each one marks a plateau where we must gather new knowledge, develop new tools, and muster new resolve before the next ascent. It tells us that the stars are not reached by a single leap, but by a long, unwavering climb, one generation passing the torch to the next, always upward, always forward into the light. Each individual limit we have discussed is a thread in a single, intricate tapestry. The cosmic speed limit of light, the crushing demands of energy, the need for indestructible hulls, the fragility of human biology, and the staggering scale of required infrastructure. These are not separate obstacles on a linear path. They form a deeply interconnected web, where a pull on one strand vibrates through all the others. This systemic view transforms the quest for speed from a series of isolated problems into a grand, multidimensional puzzle of optimization. Consider a hypothetical breakthrough in material science. Imagine we finally master the manufacturing of macroscopic sheets of perfect graphene or self-healing diamondoid composites. This is not just a victory for the hull department. A lighter, stronger hull immediately reduces the mass the engines must push, easing the energy burden dictated by the rocket equation. That saved mass could be allocated to more powerful reactors, thicker radiation shielding for the crew, or larger living spaces to ease psychological strain on a decades-long voyage. One advance in materials ripples outward, loosening constraints in propulsion, human factors, and mission architecture. Conversely, a leap in propulsion efficiency has cascading effects. A more efficient engine, perhaps a stable fusion drive or a scaled-down antimatter system, requires less fuel mass for the same journey. That reduction in fuel mass means the ship can be smaller overall, which makes building the revolutionary hull we just imagined more feasible, as we need less of the impossible material. It also reduces the cost and scale of the orbital infrastructure needed to construct and fuel the vessel, nudging the economic equation toward possibility. The artificial intelligence guiding the ship is the nervous system that ties this entire web together. A more capable, energy-efficient artificial mind can navigate more precisely, avoiding hazards that would require heavier armor. It can optimize engine performance in real time, squeezing out every fraction of a % of efficiency from the propulsion system, which again saves mass and energy. It can manage the closed life support ecosystem with perfect balance, reducing the reserves needed for a human crew. In this way, advances in computing and machine learning don't just sit alongside advances in physics and engineering, they actively amplify them. This reveals a profound truth about our endeavor. The absolute speed of a future spacecraft is not a number we will discover written in a physics textbook. It is a value that will emerge, a property that arises from the synergy of a dozen different fields pushing against their own limits in concert. It is a holistic peak where the best possible hull meets the most efficient possible engine, guided by the most intelligent possible mind, all within an economic and social framework capable of sustaining the effort. Isolating any one factor, pouring all our resources into just building a better engine while ignoring the material science of the hull or the psychology of the crew, is a path to dead ends and elegant failures. Understanding these interdependencies is our most crucial strategic tool. It tells us where to invest, which foundational breakthroughs will have the widest ripple effects. It grounds our wildest visions in integrated reality, showing that the road to the stars is not a straight line, but a vast collaborative network of human ingenuity, where every discipline has a voice in the final design. The symphony of the starship will be written by physicists, engineers, biologists, psychologists, and computer scientists together, each note essential to the harmony of the whole. The tapestry of limits we have woven is not a cage but a canvas. Our exploration through the physics that define the absolute speed of future spacecraft reveals a universe of both stern constraints and breathtaking possibilities. We have seen the unyielding constant of light speed stand as a cosmic checkpoint, a reminder that some rules are written into the bedrock of reality itself. Yet, alongside that firm barrier, we have wandered through speculative realms where warp drives might fold space and wormholes could stitch distant points together. This contrast is crucial. It shows us that the barriers we face are as much about our current understanding as they are about immutable laws. Each limit, be it the relativistic wall of infinite mass, the energetic nightmare of the rocket equation, or the biological fragility of the human body, is not a stop sign. It is a challenge, a specific and detailed problem that dares us to innovate, to collaborate, and to dream on a grander scale. The history of human progress is a story of reinterpreting limits, not merely accepting them. We once thought the sound barrier was a physical wall that would tear aircraft apart, until we understood the transonic regime and designed shapes to slip through it. The cosmic speed limit may represent a similar kind of threshold, one that demands not a bigger push but a smarter path. While we may never break the ultimate rule of light speed in the conventional sense of raw velocity through space, we may learn an elegant dance around it. The future could belong to those who learn to bend spacetime itself, to harness the subtle quirks of quantum fields, or to navigate hidden dimensional geographies we have only begun to theorize. This means the future of interstellar travel is not a pre-written script. It is an open manuscript waiting for the bold minds who will blend the rigor of physics, the ingenuity of engineering, and the boundless fuel of human imagination. The equations exist, the principles are known, but the synthesis, the act of building a bridge from theory to reality, awaits its architects. As we look to the stars, let this be our guiding thought. Every limit is an invitation to discover something new about our universe and about ourselves. The ultimate speed we achieve may have less to do with megawatts of thrust, and everything to do with the velocity of our collective ambition, the pace at which we choose to learn, build, and reach together. Thank you for joining this voyage through the fundamental frontiers of speed. If you enjoyed contemplating these cosmic boundaries, consider subscribing for more deep dives into the future of technology. I would love to hear your perspective. Which of these limits do you think we will creatively overcome first? Share your thoughts in the comments below.